Hello class, welcome to chapter 5. This is continuous random variables. So in chapter 4 we saw discrete random variables and some examples of those distributions were binomial and Poisson. Here we look at continuous random variables and we'll be looking at specific examples from normal distribution, uniform distribution. Again, let's do a quick recap. If it is a discrete random variable, if x is a discrete random variable, let's say the example was x is the number of books, right? Meaning it's countable. If x is continuous, then it has to be measured. It cannot be counted. So you could say x is the weight of a book. So then it would be an answer that can be in decimals or fractions, whereas the number of books can't be in decimals. You can't have 1.5 books or 1.79 books and so on, right? So that was a big difference. So if you looked at the functions, the probability density functions, so this was the x, the variable, the random variable, and this was p of x. So a quick recall, we saw the bingo example, the soccer example, all of those, what happens is, even in that graphical example, so say when x is 0, your probability could be somewhere here. When x is 1, the probability was somewhere there. I'm putting the dot there so that you can correspond it to the p of x function. Then you had 1, then you had 2, or something like that. I'm just writing something, I'm just making up my own, okay? And that's it. After that, it was all very, very close to. So you can see that you can roughly draw a bell-shaped graph around this, right? It is right skewed, it seems. But what I want you to see here is, if I added these dots, right, which correspond to the p of x, all these p of x, sum of all the p of x must be equal to 1, isn't it? Because all the probabilities should add up to 1, thus telling that we exhausted all the random variables and their corresponding probabilities. So they were discrete, they were separated, jumped from 1 to 2. On the other hand, when we talk about continuous random variable, as the name says, it will be one continuous flow of a graph. So the graph will flow continuously, if I'm using a similar example as above. So it flows continuously such that you do have a continuously shaded portion that accounts for the entire probability as opposed to the individual probabilities, right? So what I want to point out here is probability. And here we said the total probability must be equal to 1. Here too, the same concept is true. So the total area must be equal to 1, which is the probability. So it should be 100%. That's what we mean, right? 1 is 100%. So we now have continuity there. So we're able to shade it, and we call it as the area because of the continuity, as opposed to how we saw them as individual values. So here you have a total area that accounts for the probability for the entire distribution. So based on that, what we see now is we are talking, because it's area, but we can talk about intervals in the area, right? So I can say, what is the probability from here to here? I can call this A and B. What's the probability between A and B? That means we're asking, what is this area between A and B? Because probability is the area in this case. You can't say that in discrete. You can only say that in continuous, because you can now see it as area. So say my graph very specifically actually look like this. And let's shade this region. Okay. And if I said, what's the probability from A to B? So to find the probability between A and B, you can see that the probability here is the same as the area. And the area here is the same as the area of a triangle, which is coming from geometry. So half times base times height. So if you know the base, which is basically your b minus a, right? That's the distance here, b minus a. And the height, if I know what this value is, depending on what the function is and all that, We can use math and geometry particularly to help us come up with this height, and then enter it here, and your probability will actually be the area of this triangle. So if we know the shapes, well and good. If the shapes follow a certain known shape, like a bell-shaped graph, then we can use details related to normal distribution. If your graph pertains to a rectangular shape, like in a uniform distribution, we can simply use the area of a rectangle to get that. So we are going to use geometry where needed. We will be using this idea of rectangles or triangles in the geometry, or we could just use the bell-shaped graph, the normal distribution function, to help us find the answer. Okay, and what we'll see also is that when we use the calculator kind of helps us to get that information. Like for instance, when I said this red shaded region, right, from A to B, to get that information, we will actually rely on advanced math, which is calculus. So it's basically the area under the curve. That's the idea in calculus. So we'll be using some advanced calculus actually on the calculator to obtain this answer. Okay, we could do this manually too, but again, remember, the calculator is meant for, especially the graphing one, is meant to accommodate advanced mathematics. Therefore, we will talk about integral, definite integral. Okay, that looks like this. So your calculator will have boxes for you to enter here, and then it'll have something to enter here, and then it'll have something like this. So it looks complicated, but what it does is this actually will produce the area between A and B. So this is where you enter A value and B value. This will be the function of this curve, right? So I'll just call it y1 or something. And dx, x is the variable you're using, right? So you will enter something like this in order to get the area. So this will be the area under the curve between A and B. All right. So that's just a gist for you to see. We will start with some simple ones like uniform distribution. And if you see any rectangular shape, please remember that you're trying to use the triangular shape. We're using the triangle formula. Maybe I'll give you a formula, an example with the triangle. That will help us. Given the graph of the probability density function, find p of 1/4 less than x less than half, represented by the shaded region, which is basically find the probability of x lying between 1/4 and 1/2. That's what that means. Now let's get into the graph here and see how the scale is, meaning how does each box measure? So this is 0 mark, and that's the 1 mark. So between 0 and 1, I have 1, 2, 3, 4. I have 4 boxes between 0 and 1. So the space between 0 and 1 is divided into 4 parts. So the distance between 0 and 1 is 1. So 1 divided by 4. So each is 1/4. This is 1/4, this is 1/2, this is 3/4, and this is a 1, right? So we can see that they're talking about the region between 1/4 and 1/2, okay? And it's represented by the shaded region. Now clearly the shaded region is a triangle, okay? So I'll just say shaded region is a triangle. And area of a triangle is 1/2 times base times height. So the base would be what this distance is, right, between the 1/4 and the 1/2. So that's nothing but 1/2 minus 1/4, because that gives me the distance between the two, okay? And then the height would be this, the height of the triangle itself. The height is from 0 to 2. So the height is a 2. So if you simplify this out a little more, 1/2 times 1/4 times 2. And obviously the 2's will cancel off, leaving us with 1/4. So the area is 1/4. But they didn't ask for the area, they asked for probability of 1/4. Interestingly, we just established that the probability of a shaded region, right, which is the area of that region, is the same as the area in this case, of the triangle. The shaded region. And therefore, the question is answered directly by finding the area of the triangle. So when you have geometric shapes, it's really easy to kind of figure that out. Okay. So here what we see is we have the graph of the probability density function is given to us. We need to find P of 1 less than x less than 6, or in other words, probability of the area between 1 and 6, because that's the shaded region there, given by the shaded region. Okay, before we move on to finding the answer to this one, I want you to take a look at this entire rectangle. This rectangle is, this length would be 9 minus 1, which is 8, isn't it? So the area of a rectangle is length times width. So the entire rectangle, not the shaded region, but the black one, the length is 8, which is basically 9 minus 1, right? So I'm going to put it that way. And the height is given to be 1 over 8, which means 8 times 1 over 8. So the 8's cancel off, leaving us with 1. If the area of the rectangle in this setup comes out to be 1, this means this is the total probability. This is the entire details presented there, and we are looking for a portion of it, a specific portion of it for our shaded region. So you must understand this entire rectangle from 1 through 9 gives you that probability 1 over 8. Okay. All right, so let's focus on the shaded region. Let's write P of 1 less than x less than 6. This is nothing but the shaded region. And if the shaded region, we can see that that shaded region is a rectangle. And if it's a rectangle, let me just say area of a rectangle, that will make it more accurate. So this probability is the same as this area, and the area of a rectangle is length times width. Now focus only on the shaded region. The length is between these two, right? So 6 minus 1. And the width is given to be 1 over 8. Width in this case would be the height. The width of the rectangle would be the height here, 1 over 8, which is 5 times 1 over 8. You're free to leave, don't have to write it as a decimal. So clearly, this comes out to be 5 over 8. The probability of the variable lying between 1 and 6 is 5 over 8. In our probability density function under discrete random variable, we would find x equals 1 or x equals 6, and we went to the table and we looked at the corresponding p of x value and we gave it off as the answer they asked. But here we are looking at the shaded region and we have to use the idea of area to answer this question. Okay. Now we just saw that in this case the area was that of a rectangle, and so we're going to talk about uniform distribution here, because uniform distributions will have that rectangular region. Uniform distribution. As the name says, something is uniform here. Something will behave uniformly. Right? So let me start off by saying, first of all, this is related to a continuous probability distribution, because it is not a distribution. Because it's not a discrete probability distribution, it's continuous because of the area. All right. And here, events are equally likely to occur. Equally likely simply means that every event has the same probability of occurring, right? They have the same chance of occurring. So that every value, meaning every x value, of this distribution has the same probability value, has the same probability, P of X value. So I wanted to quickly take you to this, the illustration I discussed right in the beginning, right? Look at this one. If it's discrete, we had all these things. If it is continuous, we had this kind of a curve. But when we say that they're because the curve is actually, this is also P of X, right? So for each value, you have the P of X values, and that's what gives you this graph. But then here, for uniform distribution, we're saying this P of X value will be the same for all values on the x-axis. So what is the situation mathematically where you have all the values having the same probability? So if all x's, and this is P of X, if they all have the same value, the only way that's possible is if the graph of a uniform distribution is a horizontal line. Meaning it's not a wavy curve or some kind of a parabola, some kind of a polynomial, but it's a horizontal line. So that if you have your variables ranging from, I think it's a different color. If you have your variables ranging from A to B, and if you are interested in the region between them, you get a rectangle by default because the graph of a uniform function is a horizontal line. So let me write that out here. Because we are talking under uniform, the graph will be a horizontal line. So now based on uniform distribution, let's take a look at some examples, bearing in mind that if it's a rectangular shape, then we can use the area of a rectangle to find the probability. When we talk about the notation, X is a continuous random variable with uniform distribution. So this is U. Remember, we did it for binomial, it was B. Uniform distribution A, B. This is important because we're trying to specify the area, the region. So you need to start at a particular value on the x-axis and end at a particular value so that the area under the curve between A and B can be measured. And so a quick description for this would be X is a continuous random variable with uniform distribution. From A to B. So the area then, right? The area, because we established it's going to be a rectangle. So the area of the rectangle for this particular region from A to B will be the base, maybe half. Okay. We say length times width, but the book also interchangeably says base times height. If that's the case, you can think of this as the base and this as the height. So it's all the same. Your base will be your length and the height would be your width. So if it's base times height, the base you can figure out by doing B minus A, right? The height will have to be 1 over B minus A, because only then B minus A times 1 over B minus A would cancel off, leaving us with 1, which accounts for the entire probability. So it has to be B minus A. The height is always 1 over B minus A. The base will be B minus A. Okay. All right, so let's take a look at this example. The amount of time it takes Robbie to go grocery shopping is continuous and uniformly distributed between 20 minutes and 45 minutes. What is the probability that it takes Robbie between 29 and 39 minutes to go grocery shopping? Okay. So the graph is given to us. In the next problem, probably we'll try to build our own graph. But here what happens is we must understand that if you put in the notation, X is the continuous random variable with with uniform distribution between 20 minutes and 45 minutes. Okay, when we build the graph, we can only do it like this. Okay, let me just show that part to you. So you know it's 20 here and 45 here. Because it is told that it's a uniform distribution, you know it has to be a rectangle over this, because this line would be a horizontal line. Right? So we know that's a horizontal line. So horizontal line is always written of the form y equals some number, right? If you recall in math, in algebra, we did y equals some number. Y equals 5 means it's a horizontal line passing through 5. Y equals 0.1 means it's a horizontal line passing through 1 on the y-axis. So here we need to find what point it passes through. For that, we have to actually compute and say, okay, this height must be 1 over b minus a. So b minus a, this is my a and this is my b. So b minus a would be 25 here. So that becomes 1 over 25. And that's what they have here already given to us in the graph. But when we construct it, we will come up with that 1 over 25. Okay. And then they say, well, in between we have 29 and 39. So the question is, what is the probability that it takes Robbie between 29 and 39 minutes to go grocery shopping? All right, so I showed you how to construct it, but now let's answer the question. So what's the probability of X, the time for grocery shopping, to be between 29 and 39 minutes? So you're only focusing on this red region, or if you go back to the original graph they gave us, it's the blue shaded region. You're only interested in the blue shaded region. So find just the area of the blue shaded region. So I'm going to come here and say area of the shaded region, which is a rectangle. And because we're using the language in the book, I'm going to call it, instead of length times width, I'll say base times height. So if we were to look at the base would be the distance between 29 and 39. So that's going to be basically 39 minus 29 to know that distance between the two. And the height is set at 125 because that will be the height of this blue graph, right? The blue rectangular region, the height is 1 over 25, which comes out to be 10 times 1 over 25. Reduce that. You can leave it as a decimal because it reduces nicely, or you can leave it as a reduced fraction. Anything is fine. And so that comes out to be the answer here. The amount of time it takes Anji to pick out a new pair of shoes is continuous and uniformly distributed between 35 minutes and 75 minutes. What is the probability that it takes Anji between 40 and 50 minutes to pick out a new pair of shoes? So now they didn't give us the graph, but they did give us some very important details. They said it's continuous and it's uniform distribution. Continuous means you'd think immediately area, right? You're trying to measure it, not count it. So it's not going to be a table of values, it's going to be the area. And then we have uniform distribution, so you know that it's going to be a horizontal line. And so the resulting graph will be the shaded region would be a rectangle. So we got all these clues here. Now let's get started on graphing this. So I know that my x would go here, and this is my p of x probability. Because it's uniform distribution, they're equally likely to occur, which means the horizontal line. We got that. Okay. So it's between 35 and 75 minutes. That's how it's distributed. Right? So I want to draw a horizontal line. And I need to find out what value, y value, or p of x value it passes through. So let's see that this is the entire distribution we have at hand, right? So if I wanted to find this height, I have to do 1 over b minus a. And so I know this is a and this is b. So 1 over b minus a will be 1 over 70 minus 35, which is 1 over 35. Now, the question actually goes further and says, what's the probability that it takes Anji between 40, somewhere here, and 50, somewhere here, minutes to pick out a new pair of shoes? So if I were to construct the region, or kind of describe the region here, so it will be this shaded region. I need to find the area of this shaded region. Okay. So let me come here and say probability of x lying between 40 and 50 minutes is the same as area of shaded region, which is base times height. You know, the shaded region is a rectangle. So the base will be this distance between 40 and 50. So it's basically 50 minus 40 times. The height is just what we found here, right? The p of x. So that's 1 over 35, which is 10 times 1 over 35. Then reduce it, 5 cancels twice here and 7 here. So we can leave a fraction. The answer is a fraction. It's 2 over 7. The amount of time it takes Jackson to do his homework is continuous and uniformly distributed between 25 minutes and 80 minutes. What is the probability that it takes Jackson between 30 and 41 minutes to do his homework? My suggestion is to pause the video and try it on your own. You really feel confident that about these problems if you do it alongside me. Okay. All right. So we have x and we have p of x. P of x is going to be a height. And we have, and remember again, there also we did x times p of x, right? For discrete, we did the column x times p of x. Here too, we have the base times height is nothing but x. Base is your x, height is your p of x. So x times p of x. Okay, now that we got that parallel, let's see. Because it's a uniform distribution, I'm already drawing my horizontal line. And I'm going to come over here and mark the starting point. So somewhere here, 25, all the way to 80 minutes. So that when I write it as a notation, it's uniformly distributed from between 25 and 80 minutes. All right. So correspondingly here, 1 over b minus a will be 1 over 80 minus 25, which is 1 over 55. So your height here is 1 over 55. You got that? Now we need to, within this box, within this rectangle, we need to measure how it, what the probability is for Jackson to do his homework between 30 and 41 minutes. Say 30 is here and probably 41 is here. Then it is this shaded region that we are interested in. We use the red box to get the height, but we are actually focusing on the green box, so the shaded region here. So probability of x lying between 30 and 41. You have to learn to write it like this, especially in your exams and all that. You'll be expected to show the work like this. So don't just present the answer, learn how to present the answer neatly, okay? So try to imitate this style of writing so we can see you're working there, which is the area of the rectangular shaded region, which is base times height. Again, for a quick variety, I want you to, realize that the base here is basically your x and your height is your p of x. You remember x times p of x is what we did, right? Anyway, so your base here would be this space here between 30 and 41, so 41 minus 30. And your height, we figured it to be 1 over 55. So this is going to be 11 times 1 over 55. That gives us 1 over 5. Now, in uniform distribution, we have a condition where there will be a conditional probability. In such situations, how do we handle it? If you recall, conditional probability means that something already happened, and based on that condition, you will find the new probability. So the familiar terminology we used was given that something had already occurred, right? So if that was the case, how do we set up our problem? So I'm going to use this example to illustrate it. Suppose it takes a child between 0.5 and 4 minutes to eat a donut. What is the probability that a different child eats a donut in greater than 2 minutes, given that the child has already been eating the donut for more than 1.5 minutes? Okay, right there, that's a classic expression for conditional probability, given that the child has already, right? So it said more than 1.5 minutes. So that's a classic idea where you see that in a uniform distribution, you have that condition. It's uniform distribution for some other clues too, like, it takes a child between this and this minutes. So they're giving you a range, and so you do have that hint there, that clue. So typically, this is how it looks. You have the x, and then you have the p of x. And the x stands for the number of minutes, right? The child finishes, eats a donut. To eat a donut. So if that's the case, then I could mark my 0.5 somewhere here and my 4 minutes somewhere there. So that is a range, isn't it? So then we'll draw a horizontal line and then figure out what that height should be. Okay. Now, when we try to calculate the function, the line, what we want to see is that even though, let me just draw this, even though it's kind of starting from 0.5 to 4, because of the condition, you want to see that the condition has to be marked first. So what is the probability that a different child eats a donut in greater than 2 minutes, given that it started eating more than 1.5 minutes? Okay, so for 1.5 minutes, the child has already been eating. So this is, say, 1.5 minutes. So your new distribution actually starts from this red mark, 1.5. I'm making it super dark. Okay, so it is from 1.5 to 4 that you're interested in. So this is your new area. Okay, this is what you will use as A and B. Okay, so your height here, or the probability P of x, is 1 over B minus A, and the B has changed, the A has changed because of the condition, right? So what would have typically started at 0.5 is now starting at 1.5. So it's 1 over 4 minus 1.5. This is 1 over 2.5. Typically we don't leave our fraction with a decimal in it. You either write it as a fraction or a decimal. You don't write both in one. So for the sake of translating that, if you were to rewrite this, that would become 2 over 5. Okay, so this mark here is 2 over 5, the height. All right, now let's go into the this is the height of the desired area now. Now we need to fix the base for this. So what are we looking for? So we are looking for what is the probability that a child eats a donut in greater than 2 minutes. They didn't say when it ends, but we know that the whole thing ends in 4 minutes, right? So now we have to mark at 2, and from 2 to 4 becomes our shaded region. So the given condition restricts your original space And within that original space, within that restricted space, you will find a particular area. So when I say restricted space, I'm talking about the space that starts from 2, from the red, from the 1.5. Okay. So I want to highlight again here. We started with this brown region, right? That was the original one they gave us. And then we went to the red because of the given condition. So this will be the conditional probability part. So 1.5 minutes. So that means we reduce that brown rectangle into the one starting at red. So red between this red and this brown. And within that, we found the yellow shaded region that was greater than 2 minutes, which meant 2 all the way to 4. So if I were to write this in the probability notation, that will be x greater than 2 minutes, right? And that would be area of shaded rectangle, base times height, and the base is between 2 and 4, so that's going to be 4 minus 2. And the height, we figured it to be 1 over 2.5, which is 2 over 5, which is 2 times 2 over 5, and 4 over 5. And so what I missed doing here was I just said x greater than 2. That would not be complete because this was just not ordinary x greater than 2. This was with a given condition, right? So the given condition has to be incorporated because it just seems like x greater than 2, but it was based on the given condition. So the condition was that x was greater than 1.5, right? Because the child was already eating, had already been eating the donut for more than 1.5 minutes. So I know it is greater than 1.5. And so probability of x greater than 2 given that x greater than 1.5 is 4 over 5. Yeah. So we had some explanation to do here. We'll do another problem and probably we'll try to get through it quickly. So we are going to reuse the Anji problem and just add a condition to it. The amount of time it takes Anji to pick out a new pair of shoes is continuous and uniformly distributed between 35 minutes and 75 minutes. What is the probability that it takes Anji between 50 and 60 minutes to pick out a new pair of shoes, given that she has already spent 45 minutes shopping? So I will walk you through all the steps. I know you are probably going to choose to skip some steps because you know the process, but I'm trying to explain it with utmost detail, so I have the whole thing. I'm going to mark from, I'll draw the horizontal line because it's a uniform distribution, and then I will say it goes from 35 to 75. That's the whole thing. But then I have the condition that she already spent 45 minutes shopping. So let's switch it then to 40, 45. So now my box would be just 45 to 75. So if I were to find the 1 over b minus a, this will be my a, this will be my b. So 1 over 75 minus 45, which is 1 over 30. So it's 1 over 30 for this position here. The height of the rectangle is 1 over 30. Okay, and then let's go to the actual probability that it takes Anji between 50 and 60 minutes. And so 50 and probably 60 here. And that would be my shaded region. So probability of Anji spending between 50 and 60 minutes, P of 50 less than X less than 60, given that she has already spent 45 minutes, okay, will be base times height. Base of the blue shaded region would be 60 minus 50 times the height we found was 1 over 30. So that's 10 times 1 over 30, which is 1 over 3. Now for a uniform distribution, because the probabilities are equally likely to occur, right? The evens, the outcomes. Therefore, every value has the exact same probability over the entire interval. And therefore, when we try to find the mean, mu, right? Mean is always given the symbol mu here. Just before that, let me clear that quickly. I wanted to show the symbolic notation here, because we just need A and B for this computation, okay? So then the mean mu will be A plus B over 2. As simple as that, because it's uniform, which means it's this box, it's this rectangle. So the mean would be, the center of that box would be the average of the end points, right? So that'll be right in the middle. So that's your mean. And standard deviation, it takes the symbol sigma, and sigma would be square root of b minus a over the whole squared over 12. Very simple. The entire formula just rests on a and b. Okay, so we'll do a quick example on this. Let x be a continuous random variable with u, uniform distribution, between 13 and 20. This represents the amount of time a person shops at the grocery store after work in minutes. What is the average amount of average amount of time a person spends in the grocery store after work? What is the standard deviation? So there are two things they're asking. They're asking for the average amount and the standard deviation. So we know that they're basically asking for the mean and the standard deviation. So x, u, 13, 20. So we know that our A is 13 and our B is 20, because this is all we need to calculate the mean. Mean mu is A plus B over 2, 13 plus 20 over 2, which is 16.5. And then standard deviation sigma is square root of B minus A the whole squared over 12. That is 20 minus 13, the whole squared over 12. And that gives you a long number, but we approximate it and say it's 2.02. That's it, as simple as that. And so we find our mean and standard deviation for the uniform distribution by using these two formulas. So with that, we come to the end of chapter 5. What I want you to really understand is that this is just an introduction to the continuous random variable. So when you look at functions, you know, if it is a uniform distribution, you know that it's going to be like this with this rectangle, and we got that, right? And if it is not a uniform distribution, the other one we're going to look at in the next chapter would be, this bell-shaped graph. So then everything under the curve would be shaded, or a portion of it could be shaded, but the entire curve would be, the area would be equal to 1, right? Like how we had the area to be equal to 1. So now these are specific shapes, right? One is a rectangle, one is a bell shape. And so they have their own specific ways of calculating them. Now, if you had different shapes, okay, meaning these are any curves, right? So you can have something like that, and then we could just focus on A to B here. So if that's the case, I should know what this f of x is. And if I'm given a function, if it comes as, I don't know, 0.15x plus 3 or something like that, then you are going to use this function to find the area under the curve using that instruction on calculus, okay? Because that's again using the calculator. I know you are not familiar with calculus. We're not expecting you to know that, but it's a shortcut that we use in order to use the calculator, okay? But that's the reason why we will not go much into this at all. We will only restrict ourselves to the uniform and the bell-shaped graph. But just a gist for you to know that these are not the only shapes you can expect. That's all I'm trying to show here. So you can have, say, a line like this, and then it could be the area under the curve, which is fine because you now have a nice rectangle. Sorry, a triangle. I keep saying rectangle. And if it is, I don't know, if it is, say, if it's a chair-shaped graph, this graph goes endlessly, but for the sake of our problem, we could fix your A to be here and your B to be here and just say find the area below this, right? So what I'm trying to illustrate here is your shape could be anyhow, but those will require a lot more mathematical techniques. In fact, we have a special branch of study for that, but we can remember that continuous distribution is meant to accommodate any kind of function, and we will just focus on these two types. All right, class. So thank you for your time here. This chapter 5 has been really, really short for us. So I'll see you in the next video in chapter 6. Bye-bye.